Welcome all of you. I am Vishwas Khare from SSR College Silvassa. In today's tutorial, we will talk about examples of matrix space. Example: does dxy defined by modulus of sin x minus y define a matrix on R justify? So here we will have to check that if dxy is defined by this definition, then this is a matrix on R or not. Solution: recall that if D is a matrix on X, then dxy is equal to 0 if and only if X is equal to Y or all xy belongs to X. So this is one of the property among the all properties of matrix on X which should be satisfied if D is a matrix on X. Now in this particular case, if we take X is equal to pi and Y is equal to 0, then dxy is equal to modulus of sin pi minus 0, that is sin pi, and we know its value is 0, but x is not equal to y. So here we are getting dxy is equal to 0, but x is not equal to y. So this property is violated. Hence, D is not a matrix on R. Again, let an example. Let D from R to R be defined by dxy is equal to x square minus y square or all xy belongs to R. Show that D is not a matrix on R. Again, recall that if D is a matrix on X, then dxy is equal to 0 if and only if X is equal to Y or all xy belongs to X. Now in this particular case, if we take X is equal to 2 and Y is equal to minus 2, then dxy is modulus of 2 square minus minus 2 square is equal to modulus of 4 minus 4 is equal to 0, but X is not equal to Y. So again, this property is violated. That is, we are having dxy is equal to 0. So what should happen? X is equal to y. But here we are having x is not equal to y. Still we are getting dxy is equal to 0. It means, hence D is not matrix on R. Again, the same example, just dxy is equal to modulus of x to the power 4 minus y to the power 4 defines a matrix on R, justify. So whether again we will have to check whether it is a matrix on R. Recall that if D is a matrix on X, then dxy is equal to 0 if and only if X is equal to Y or all xy belongs to X. Now in this particular case, if we take X is equal to 1 and Y is equal to minus 1, then dxy is equal to modulus of 1 to the power 4 minus minus 1 to the power 4 is equal to modulus of 1 minus 1 is equal to 0. But again, X is not equal to Y because X is equal to 1 and Y is equal to minus 1. So this property is again violated. So D is not a matrix on R. Next example, does dxy is equal to modulus x plus y define a matrix on R? Justify. Again, recall that if D is a matrix on X, then dxy is equal to 0 if and only if X is equal to Y or all xy belongs to X. Now in this case, if we take X is equal to 1 and Y is equal to 1, then X is equal to Y because both are having the value 1. But dxy is equal to modulus of 1 plus 1, which is 2, not equal to 0. So what should here happen? If x is equal to y, then dxy should be equal to 0 by this property. But here in this case, x is equal to y, but dxy is not equal to 0. Hence, D is not a matrix on R. In the previous 3 examples, we have seen that this property is violated. But it is not necessary that in every example you will find that this property is violated. Recall, if D is a matrix, then there are 4 properties which should be satisfied. So any of that 4 properties is not satisfied, then we will say that D is not a matrix on a given non-empty set X. Now let D is equal to R dash cross R dash to R is defined by dxy is equal to modulus of 1 upon x minus 1 upon y or all xy belongs to R dash is equal to R minus 0. Show that D is a matrix for R dash which is equal to R minus 0. That is, what is R dash? R dash is non-zero real number. Solution: clearly dxy is equal to absolute value of 1 upon x minus 1 upon y is greater than equal to 0. Because modulus or absolute value of any real number is greater than equal to 0. 1 upon x is non-zero number, 1 upon y is non-zero number, so 1 upon x minus 1 upon y, it is a real number and its modulus will always greater than equal to 0. So dxy is greater than equal to 0. Now second property, dxy is equal to 0 if and only if modulus of 1 upon x minus 1 upon y is equal to 0, if and only if 1 upon x minus 1 upon y is equal to 0, because if modulus of any real number is 0, then that real number should be equal to 0, if and only if 1 upon x is equal to 1 upon y, if and only if x is equal to y. So ultimately we got dxy is equal to 0 if and only if x is equal to y. Third property, dxy is equal to 1 upon x minus 1 upon y, this can be written as 1 upon y minus 1 upon x, which is same as by definition d of yx. So we got dxy is equal to dyx. Now fourth, let z belongs to r dash, then dxy is equal to by definition 1 upon x minus 1 upon y, absolute value of this, which is same as modulus of 1 upon x minus 1 upon z plus 1 upon z minus 1 upon y. But by triangle inequality, this quantity is less than modulus of 1 upon x minus 1 upon z plus modulus of 1 upon z minus 1 upon y, which is same as by definition this is equal to dxz plus dzy. So we got dxy is less than equal to dxz plus dzy, and so all the properties satisfied. So D is a metric on R dash and R dash D is a metric space. Now let example. Let x be a metric space and k greater than 0 be a fixed number. For xy belongs to k, show that d to the power k xy is equal to k times dxy defines a metric on x. Again it is very easy, as k greater than 0 and d is a metric, so d to the power k x comma y is equal to k times d x comma y is greater than 0. Because k is already greater than 0 and dxy is a metric on x, so value is greater than equal to 0. So product of these two is greater than 0. So we got d to the power k xy is greater than equal to 0. Second, d to the power xy k xy is equal to 0 means k times dxy is 0 if and only if dxy is equal to 0. Why this is so? Because k is greater than 0. So k times dxy is 0 gives dxy is equal to 0. This gives x is equal to y because d is a metric. So conversely also, if x is equal to y, we get d to the power k xy is equal to 0. Third property, d to the power k xy is equal to k times dxy can be written as k times dyx because d is a metric. But by definition it becomes d to the power k yx. Now fourth, let z belongs to x, then d to the power k xy is equal to k times dxy, which is less than equal to k times dxz plus dzy using the triangle inequality of D. What is D? D is a metric on X. This is same as k times dxz plus k times dzy, but by definition this becomes d to the power k xz plus d to the power k zy. So ultimately we got d to the power k xy is less than equal to d to the power k xz plus d to the power k zy. Hence D is a metric on X and xd is a metric space. Now let us take this example. Let xy belongs to R, define dxy is equal to 0 if x is equal to y, and it is modulus x plus modulus y if x is not equal to y. Then D is a metric on X. Solution. Clearly dxy is greater than equal to 0 because dxy can take any two values 0 or modulus of x plus modulus of y. So in any case it is greater than equal to 0. Now dxy is 0 if and only if x is equal to y. This is by definition that dxy is 0 if and only if x is equal to y. Third, if x is equal to y, then dxy is 0, but in this case dyx is also 0, so dxy is equal to dyx. And if x is not equal to y, then dxy will be modulus x plus modulus of y. This can be written as modulus of y plus modulus of x. This gives dyx because this is the definition of dyx. Fourth property, let z belongs to R. If x is equal to y, then dxy is equal to 0. So left hand side is 0 and right hand side, these two are non-negative quantities. So this holds that dxy is less than equal to dxz plus dzy or dyz. If x is not equal to y, then dxy is equal to modulus of x plus modulus of y. Now if z is equal to x, then z cannot be equal to y, because if z is equal to x and x is not equal to y, so z cannot be equal to y. This implies dxz is equal to 0 and dzy is modulus of z plus modulus of y. So dxy becomes modulus of x plus modulus of y, this is by definition, which is less than equal to mod z plus mod y. because x is equal to z, so modulus of x become modulus z. This quantity is same as modulus of y plus modulus of z, which is equal to dyz. And dyz is less than equal to dxz plus dyz, because dxz is a non-negative quantity, so dyz is always less than equal to dyz plus some non-negative quantity. So ultimately we got dxy is less than equal to dxz plus dyz. Similarly, we can prove the result if z is equal to y and z is not equal to x. Now if z is not equal to x and z is not equal to y, it means z is a different point which is not equal to x and not equal to y. Then dxz is equal to mod x plus mod z and dyz is equal to mod y plus mod z. This is by definition. So dxy is equal to mod x plus mod y, which is less than equal to mod x plus mod z plus mod y plus mod z. Which ultimately means this expression is less than equal to this expression, because mod z are non-negative quantities. But this by definition mod x plus mod z becomes dxz and this becomes dyz. So ultimately we got dxy is less than equal to dxz plus dyz in this case also. Hence D is a matrix on R and RD is a matrix space. This is the reference P.K. Jain, Khalid Ahmed, matrix space Narosa projection. Thank you very much.